Hey everyone, welcome back to the Pod 4 Journal Club. I am seriously so pumped you're here today. If you're new to the channel, definitely take a second, check the description below, and hit that subscribe button to join the club. Today, we've got a truly fascinating explainer for you. We're digging into a brand new research paper that asks just a massive, fundamental question about the future of artificial intelligence. It's a study that totally pushes past all the hype of, chatbots and asks what these models can actually do when they're really put to the test. So here's the core of it. We all know that large language models are great at writing essays, generating code, acing standardized tests. But can AI models actually do real science and apply it to engineering, like out in the real world? That is the central curiosity gap of today's paper. We are basically going to take a journey straight into the problem-solving mind of artificial intelligence to see if it can independently discover how a world works, and then use those discoveries to build complex, functional tools from scratch. To figure this out, we're going to follow a really clear roadmap today. 1. The AI science gap. 2. Minecraft as a lab. 3. The 26% plateau. 4. What the study missed. And finally, AI's next big hurdle. Let's get right into it. All right, Section 1. The AI science gap, mapping the unknown. Okay, so there is this massive fundamental leap between an AI simply memorizing facts from the internet and actually engineering real-world solutions. I mean, knowing the dictionary definition of gravity is way different from, actually building an airplane. The researchers frame this whole challenge around something they call the discovery to application loop. Basically, this is the process of discovering causal regularities in the world, like figuring out how physics or mechanics actually work, and then applying those rules to build functional systems. Throughout human history, this loop of science and engineering has been the absolute engine of our technological progress, right? It's literally a hallmark of general intelligence. So to really test an AI's capability, we have to see if it can successfully navigate this exact loop completely on its own. Which brings us to Section 2, Minecraft as a lab, the SCICRAFTER benchmark. Now, you might be wondering, why not just use physical robots? Well, there's a huge complexity gap in the real world. Physical robotics are just incredibly difficult to control, they're slow, and they're expensive. Researchers needed a virtual surrogate, a sandbox that isolates the cognitive processes of scientific inquiry from just the physical clunkiness of real-world robot arms. And that is exactly where the SCICRAFTER benchmark comes in. Now, what's really interesting about this visual is how it shows the progression. The AI is tasked with igniting lamps in specific patterns, like turning them all on at the exact same time. Sounds simple, right? But these tasks scale up in complexity. Synchronizing 4 lamps? Easy. But synchronizing 16, 32, or 64 lamps over a large distance? That forces the AI to encounter completely new physics problems. It can't just regurgitate a memorized solution from its training data. It has to genuinely experiment, observe its failures, and discover entirely new topological designs to make the whole shebang work. To actually do this, the AI uses something called redstone. Now for the non-gamers watching, let's just bust the jargon real quick. Think of redstone as essentially Minecraft's programmable circuitry system. It acts as a perfect stand-in for real-world electrical wiring and physics. And it's got strict rules. Signals lose strength over distance, connections have to be routed exactly right, and the components themselves actually add time delays. The AI absolutely has to master this specific environment if it wants to succeed. All right, Section 3, the 26% plateau, where models hit a wall. So the researchers equipped the absolute cutting-edge models with an agent scaffold, which basically gave them the ability to write code, press buttons in the game, and observe the results of their actions. But what they found was honestly pretty shocking: 26%. That was it. Even the absolute best frontier model they tested maxed out at a mere 26% success rate across these scaling challenges. Crazy, right? When you look at the data, you can see exactly how the major players stacked up. Gemini 3 Pro hit that 26%. GPT 5.2 was right behind it at 25.5%. Claude Opus 4.5 came in at 21%. And what this tells us is incredibly important. It means that simply scaling up model size, just throwing more parameters and compute at the problem, isn't solving this fundamental bottleneck. They all hit the exact same wall. And this brilliantly illustrates why. Instead of just throwing their hands up and saying, well, the AI failed, the researchers actually reverse-engineered the failures. They broke the AI's mind down into 4 distinct testing capacities to figure out exactly where it was failing in the scientific process. They broke the scientific method sequence into 4 specific steps. Step 1, identify knowledge gap. Basically, realizing what you don't know.
Step 2, experimental discovery, actually running the tests to find the answer. Step 3, consolidate knowledge, writing down what you learned so you don't just forget it. And step 4, apply knowledge, taking all that and building the final device. To figure this out, the researchers cleverly used what they called oracle hints, which is basically giving the AI a subtle nudge about what to look for. And they used specific scientist subagents to isolate exactly which of these 4 steps was tripping the AI up. Just look at this real failure case from the study. The paper calls this an application gap. The AI built this massive 32-lamp structure. And, to a human just glancing at it, it looks symmetrical, it looks pretty logical. But the AI placed the repeaters, those little gray boxes that boost the electrical signal, facing backward. They're literally acting as roadblocks. So the signal is completely blocked to 24 out of the 32 lamps. The AI gathered the right components, sure, but it fundamentally failed to apply the physics to actually make it function. So the absolutely crucial question is, how do we fix this? Well, when looking at that third step, the knowledge consolidation gap, the researchers found something super fascinating. If you just let the AI take free-form, unstructured notes on what it discovered, its success rate sat around 58% under the best assisted conditions. But if you force the AI to structure its notes like a real scientist, making it write down a specific claim, the proof, the constraints, and an example, its success rate jumped to 64%. It's like a giant puzzle. Just like a human student, organizing the information logically drastically improves an AI's ability to actually learn something and apply it later. Moving on to Section 4, what the study missed, blind spots. Because, hey, a good journal club always acknowledges the boundaries of the data, right? We have to be rigorous here. The authors are very clear about their blind spots. First off, Minecraft is still a synthetic environment. It is incredibly clean, it completely lacks the messy, unpredictable noise of, say, a real-world biology or chemistry lab. Second, these tests relied heavily on a specific coding scaffold called Claude Code to let the AI interact with the game. A different, purpose-built architecture might actually perform a lot better. And finally, giving the AI those oracle hints during testing might have artificially triggered it to explore, kind of inflating some of the capability metrics. So this 26% baseline isn't necessarily the absolute ceiling of what these models are capable of. It's really more of a diagnostic snapshot of exactly where they are today. And that brings us to our final section, Section 5. AI's next big hurdle, raising the right problems. So, what is the most profound, real-world takeaway from all this data? Well, the researchers realized that as models get bigger, their basic application skills are getting better. But the new, massive bottleneck? It's that very first step, knowledge gap identification. It's the ability to look at a broken system and actually ask, okay, what exactly am I missing here? The paper connects this directly to a famous piece of wisdom paraphrased from Albert Einstein. The formulation of a problem is often more essential than its solution. Posing effective questions demands a level of true discernment that, frankly, current AI just doesn't have yet. So I want to leave you with this provocative thought to chew on. As we continue to scale these massive systems, are we just building AI that acts as a really fast problem solver, or are we actually building AI that knows which problems to solve next? Because that right there is the true frontier of general intelligence. I would absolutely love to hear your thoughts on this, so please drop a comment below and let's discuss. Thank you so much for joining this explainer. And remember, if you enjoyed this structured breakdown, please check out the description and subscribe to Pod4 Journal Club so you never miss our next deep dive. Keep learning, and I will see you next time.